candidate with UC Berkeley, with Professor Peter Rabir, is that correct?
Yeah.
Yeah. He graduated from Australian National University, and he worked with Professor Richard Hartley and Ian Reid, and he already has, before starting his PhD, numerous publications in very strong venues. So, welcome to you.
Thank you for the introduction. So, today I'm going to talk about something about embodied reasoning. So, there are lots of forms of embodied reasoning. It's a huge topic, and I'm going to talk about like how can we paving the path towards the generalized embodied reasoning. So, I'll begin with a quote. I think that's 2022. That's a very long time ago. That Peter Bell gave a talk at Skill AI. So he said, I'm really excited to see whether we can build generalizable robotic system with a single large neural network that can quickly learn new skills similar to what we already have seen in computer vision and natural language processing, which is LMs. So once both components, logistic network foundation model, I think what he mentioned logical network, especially the foundation model today, we are using every day, and this logical network, if well optimized, will be highly prepared to acquire new skills very quickly. These skills can be learned through imitation learning, which is the basic, very foundation RL method. From human demonstration, you can gather human data from there, and a very quick method for RL that's called reinforcement learning with a specified reward function. That's basically the RL VR today. With the verifiable reward. So, and we're reinforcement learning from human, that's RHF, in a loop, who provides example to guide the learning process in the right direction, and something about it. So what he talked about is that a RL method or RL trajectory that could be help with the foundation model or logical network that what he referred to make the model have more generalizability in different areas. So you can see a very promising trend from specialized method to general method in both spatial intelligence and embodied, which is previously most of these works are focusing on how to get one task pretty good. For example, there are 3D COCA, which is working on like how to doing captioning of the 3D scene, and there are lots of 3D reconstruction work. You're coming from SFM to nerve to Gaussian to nowadays we are using a feed-forward network to get a 3D scene very quick. But these methods have been now moving forward to the general method, which is one model or one foundation model capable handling of multiple tasks. For example, 3DR1 is the work I'm doing last year, but this year in Europe get a very good feedback. So it's a foundation model that can handling various scene understanding tasks, which I'll go through later. And there's a NavR1. It's also a reinforcement learning based navigation method that can navigate to different scenes given different conditions. For example, visual objects or languages. And also you can working on reinforcement learning on visual language action model, the VLA model, and also word model, which is I'll go through later. So just some quick recap of the 3D specialized method. So we started our spatial intelligence point from a representation learning perspective because that's one came from, like computer vision representation learning. So I'm thinking one thing last year, that can we learning something just like what we did in the computer vision area, that if we can gather sufficient data, which is pairwise data of the scene and caption, can we learning something with representation with the spatial information? For example, I gather pairwise point cloud and caption data and fit into a clip-like structure. Does the model provide good representation for us to caption the scene? So this is basically the work did. And you can see even we just directly, not really apply, but adapt a traditional computer vision representation learning method to the spatial domain, it can still work very well. So Vote-to-cap DTR is a traditional method, which is two stages. You have a dense prediction head, that's DTR, right? So you can do dense prediction, then doing caption. So this is the very basic method for baseline for 3D captioning. And ours method has showing that given a sufficient pairwise data, we can do a 3D representation learning and outperform the traditional way to do that. So that's basically 3D COCA. And do we need those kind of large data in terms of reinforcement, in terms of representation learning? The answer is no. Is that we don't need. It doesn't mean that we gather more data to scale more performance is the correct trend. Instead, we need to gather more high quality data to scaling the method. So this work, DCC, which is data central learning, told us that we don't need to scaling infinite data for doing 3D representation. We just need the high quality part. So we only take the top 75% of the high quality data, and we can achieve almost the same or even better performance than the full data baseline. So basically, that's gave us some intuition. Yeah.
Can you tell us what high quality means?
Yeah, that's very good. So there's a lot of critics about the quality. So if you're doing something between the visual modality, no matter you're doing 2D or 3D, and between a language modality, the most important critic is the alignment between the region and the text. So the first critic for filtering those data will be the basic CLEAP score of these data, and another threshold for you to filter those noisy data is about the quality about the point cloud. You have a lot of measurement or a lot of method to measure if a point cloud is good. So you can render into images. You can fit into a small language models. For example, Queen VL nowadays are very good to see if the point cloud is clean or not. So so basically, I believe like two thresholds to help you to filter these data. One is the alignment between the modality. One is the if the visual modality preserve good geometry and quality. So basically, that's two thresholds. Yeah. So yeah, this work is just a expansion. That's a IGCV under review paper, so-called 3D COCA V2. That's another early exploration of how can we adapt a well-pretrained foundation model, especially a representation learning model, to a scene that is out of domain, that is out of your training domain. For example, if I train a 3D COCA model on a indoor point cloud pairwise data, but I want to test it on the street, for example, on the self-driving scene, most likely it will fail if you're not doing any adaptation. So there's a very elegant way that's nowadays using been well used in LLM in language community that's called chain of thoughts, right? So chain of thoughts is basically let your language model to output more tokens, to decode more tokens, and those tokens consist of the chain of their thinking. So it's similar to a visual language pre-training in the 3D domain. Is that if you're doing some searching, for example, I'm having the output, for example, n candidate output, and I have some criteria to choose the best of n candidate. It will eventually have a better adaptation to a new scene. So it's a very basic idea that's learning from the language models. And yeah, I really like the what Philippe from MIT, Professor Philippe from MIT said. He said that chain of thought is actually a searching method of the language models, because previously the language without chain of thought we are doing beam search in the language models, and nowadays we have chain of thought. We can using the model internal in-context learning capability to do searching. So this method has impact on the 3D VLP, 3D visual language pre-training. So basically, I just go through the traditional way to do that. And what's next for a 3D embodied foundation model? So there's a couple questions that we need to solve. So the first question is, like, how can we achieve zero-shot generalizability across different tasks given the domain knowledge gap between them? Like, how can we adapt this domain knowledge gap? And the second is, how can we adjust the foundation model after the conventional supervised post-training or a self-supervised learning? That's what I'm just going through. And when the outcome are not unsatisfactory on specific tasks, for example, I'm training a very good caption model, but I want to use it for navigation, it's just non-satisfactory. How can we do that? And the third part is, like, how can we ground our foundation model into physical world? How can I do this sim to real stuff? And the most importantly, like, what if I just don't have a very good supervision? You know, RL is something about human bias, right? If you're a human expert very good, you're designing very good reward, that the model could somehow, if you have sufficient data or sufficient training, the model can perform good. But sometimes that it's just hard to design the reward function or the reward signal. And how can we let the model to do, let the robot to do self-evolve? That's another topic. Yeah. So basically, that's what I'm going to talk about. So first part is how can we enhance the generalizability of foundation model? Here's a hint. So synthetic data helps to enhance the generalizability. So we have already done the traditional way to do the 3D representation learning. That is, if we have sufficient high quality regional language pre-training data, then we can pre-train a very good representation. So how can we gather these data? I mean, from a traditional way, we just download videos and images from the web, or having interns as a teacher to record the egocentric or isocentric videos, right, for training data. But that's not really effective or efficient. So one way to do that is doing it via synthetic data. So we already know that language model has a very good capability on learning the abstraction of human knowledges. So I'm not supporting language models. Actually, I'm against language models because it can only understand languages. But the good point from the language model is that languages is the abstraction of the human knowledge. So if we can use this point to use the language models as a data engine to synthetic more data, to help us to build a high quality data for our embodied model training, then it's a good stuff. So one way to do that is called a COT data engine. Is that we have some goal for our synthetic data. For example, we want the model to have better Q&A performance, right? We want model have a better response in terms of answer. So we use a frontier. In that time, that was a Gemini Pro, and now we have like cloud, right? So you use this foundation model, use this language model to synthetic more data to follow the form that we want to use. So if we can gather sufficient and more very diverse data to use it to train a foundation model, it will generalize good. And it's more efficient in the academia, because in the academia you don't have too many interns to help you to collect data, right? So use synthetic data, and these stuff have been already used in the industry. I believe Google when they developed Jenny, they started using synthetic data even in the version 1, I believe, and now it's just a like very standard procedure. And for example, if we want to develop a generalizable 3D foundation model that can handle in different tasks in terms of scene understanding, we just gather these data. So we gather some, let's say, spatial relation. That's basically the relationship between the objects. For example, I don't know, this is the speaker, right? It's a speaker on top of the table. That's a spatial relation. So this, you know, if you recall it a little bit, this stuff is actually the scene graph that people started working on like a couple years ago. And but nowadays they're not calling scene graph, they're calling spatial relation, just getting this kind of data. And also the color, location, other stuff like existence count. If you're getting sufficient data, it will perform very good on different tasks. For example, DC means instance captioning. Okay. That means that the object is being detected with the dense prediction, and and also being captioned, which is I have some demo later. So 3D planning, 3D reasoning, dialogue, visual grounding, Q&A, object captioning. So yeah, so you can see that once we gather very diverse data, we can train a foundation model that can handle these tasks. And here are some examples. I'll just show the examples and I'll get back to the RL part. Yeah. So in this case, you will know that what kind of task is this. So yeah, that's a dense captioning task. You know, just finding detecting the object and give it a corresponding caption. And these are all unseen environment. These are zero shot. So this is also the object captioning. That is, I told you where's the sofa, but you need to give me the description of the sofa, and also the visual grounding to figure out where's the what is the, let's say, sorry, okay, played it, yeah. Where's the cabinet? Yeah, cabinet. Yeah. So also the Q&A. You can asking some questions to the foundation model, and it will give you the response. Also the dialogue, just chatting with the bot. And reasoning. I believe reasoning and planning are similar thing, but in the domain, in the community, they're trying to let's say differentiate them, but they're just the same. So reasoning is basically to let the model reason and to tell what kind of what is the correct answer to your question. So plan is, for example, I want to organize the room. Like, how can we do that? Can you give us a plan? I believe like reasoning and planning are the same thing. But here's the problem. Like, after I pre-train a model, it looks very good. You can see the zero shot method, zero shot capability looks very good. But in some cases, for example, I want to detect a very tiny object on the table, but it just cannot ground it. And for another thing, probably like if the room is very dark, there's no lighting. Like, how can I adjust the model in a very low luminous room? Like, how can we adjust this? So foundation model pre-training using self-supervised data and supervised fine-tuning will gives you 90% of satisfactory scenario, but there's always going to be 10% that you are not satisfactory. So in this case, RL is the choice. So here's a very simple way that we can do in the academia. That's called reinforcement learning with verifiable reward. So RLVR compared with the traditional imitation learning and RLHF, they're much more cheaper and quicker. So for example, if we're using imitation learning, you need to gather a lot of large-scale real human interact with objects. So that's time-consuming and expensive. And also with the RLHF. So RLHF is human needs to give the feedback of the outcome as a reward, or RLAIF, which means you need to rent to buy the API of the language models to give you a reward. But RVR does not need this. RVR just simple reward function that can help with the let's say with the performance. For example, if I found that some tiny object that cannot be detected, that's very easy to address. Is that you're using a perception reward? Like, just calculate the IOU and the performance will be great. But this will gives you another problem. Is that there's two experience, or let's say there's two takeaways of these RLVR. Is one is that reward function should not be complex. Most of the time, complex reward function is not working. Simple reward function works better than complex one. That's the first part. Second part is do not use your evaluation criteria as the reward function. That will cause reward hacking. So if you avoid these two, then another part you need to address is the optimization conflict between these reward functions. But I'm not going to talk about this in this talk because it's something I'm currently working on and I haven't addressed this. Is that if you're multiply, or not really multiply, but adding different rewards, during the optimization, the reward direction is in a conflict. So there's always going to be 1 + 1 less than 2. So if you're doing let's say perception reward only, you will get a very good perception. But if you're adding up these two, the perception capability will decrease a little bit. So that was called reward conflict. So one way to do that is called on-policy distillation. I'm currently working on that. I haven't got a very good results, but that result should be working probably like ACFR. Let's see if it works. But so you can see after RLVR, all the zero-shot capability, I think that's zero-shot, yes. Zero-shot capability has increased a little bit. And this, for example, this dialogue is largely increased because I think the CLIP score is currently working on that. So yeah, so every perspective of the capability has been increased a little bit. And if you're, which means that RL is working. So if you're design a very good, very effective reward, then it should help. So yeah, so.
What was the first one, the SFT?
Yeah, so SFT zero shot is called like we pre-train our model on these CN30K, that's 30K data, and I'm not doing any RL. So I just directly let it to do zero shot on a unseen data. So it performed like the gray bar. Yeah, it's just let's say theta is a criteria. So you can see it's basically lowest performance in this setting. And RL zero shot just we doing RL, but we are not fine tuning on the similar data. For example, I'm applying my 3DR1 model on a indoor room, but I'm pre-training on a, let's say I'm applying on the office, but I'm training on a home environment. So I don't have any data that is related to the office. So I'm doing a zero shot scenario. So these are the yellow bar. And the fine tuning, which means that, let's say I have a office environment data set, and I divide it to like basic training and validation set. So I'm training on the training and evaluating on the validation, and it will give you like the green bar, which is the best. So yeah, so but at least you can see even with zero shot, the RL is slightly increasing the performance. Yeah. So that's basically the architecture of the 3DR1 model, which is you have a different modality encoder, and you have a different modality decoder. You can get the dense prediction. You can also get the text response. So it's a unified model. Yeah. So I just go through these results, and here's a video. Okay, here's the video. So there is something wrong with the visualization because I think because the visualizing code is wrong and the bounding box is floating. But basically, those visualization is those prediction is pretty much correct, and these scenes are based also is download from the web. I think it's download from a TikTok video. They doing panning video of a new room. They're trying to sell the room, right? Sell the apartment. So we just doing a zero shot prediction on these unseen environment, and it looks like this. Yeah, it's pretty good. But just the visualization code has some problem just floating. Yeah. But here's the question. Nowadays, like 90% people, especially in embodied AI and language models, they're trying to use RL because they believe that RL is the most frontier work, which unfortunately RL has been developed like 20, 30 years ago. But they still believe that RL is the most correct way to do that, and they try to use RL from like end-to-end training for their work. But this is not correct. The community has two views on that. So first view, for example, OpenAI and the language model community believe that the foundation models should be trained RL from scratch, which means that you have a randomly initialized method and you should use RL all the time. But this creates a problem, is that RL does not give you a new capability. For example, those understanding capability are actually acquired from the those understanding capability are actually acquired from the SFT stage instead of the RL stage. So RL stage is basically enhance their capability instead of activate those capability of the model. So that's the one problem. And the second problem is RL is very expensive. So even with the RLVR, I will show you later in the world model, it still takes a lot of time in the reward and the rollout stage. So RL is not a really good training method from scratch. And the third part is RL will probably gives you a tunnel vision of the model. So what it means by tunnel vision is that the model will be performing very good on this reward direction, but not very good in those, yeah.
Just can you clarify if this is only for the scene understanding?
No, it's for everything. I'll go through that navigation. That's the navigation work, and that's our mobile navigation and manipulation work, and this one is the work model work. So everything basically, yeah.
Just to have a context.
Yeah. So but there's still industry that believe that RL should be trained from scratch. So for example, OpenAI, right? You can see a lot of OpenAI researchers, especially principal researchers, talking about that an inverted cherry cake, which is the RL as a cake base and only SFT as a topping, which is like from my perspective is very crazy. And there's another way that there's another view that RL should not be used for training. For example, this is the SML paper, which is I believe is correct, and also Yan and Kun believe is correct, because what Yan and Kun claim is a click analogy, which is the self-supervised learning without any data should be the base of the cake, and the supervised learning with some high-quality label data should be the let's say the icing of this cake, and the RL should be only the cherry. So RL should not be let's say be the main part of the training. Well, I believe Yan Kun agree with that. I believe Liaosha agree with that. I'm not sure if Peter agree with that. I think Peter probably gonna agree with that, because what he mentioned in the paving path towards generalized robotics is a similar idea. But yeah, so I suggest that do not use RL for pre-training, but only use RL for adjusting your foundation model if some part of it is unsatisfactory. So that's my suggestion. So yeah, so is the previous method also capable in the real world robot? For example, navigation task. I'll say yes, it is. So the another problem is, how can we adapt these 3D foundation models? We have a very good data synthetic pipeline. We have a very good 3D foundation model pre-training, and how can we adapt it into real world? How can we let the robot to reason like a human level intelligence, like a real human? So something I got inspired from the psychology is that what Daniel said is the division between the labor system 1 and system 2 is highly efficient. So if we can somehow have a better or more fine-grained design of our model that can handling our, let's say, that can handle real-time scenarios in a very agile way, which means that we don't need to fill every high frequency data. For example, the real-time image frames from the camera, the point cloud, the real-time point cloud to the whole network, but only fit into the system 1. And we have a system 2 as a long-term memory as a slow model, but as a long-term memory to realize what's going on for the whole environment. So that will be help. So that VAR1 is exactly what we try to do. So this work is for adapting 3D R1 or 3D R1 similar style like kind of work to the embodied navigation. So basically, this model is the identical model that's pre-trained initialized by the 3D R1, but we did some fine-grained design. So we realized that if we try to fill everything, like egocentric views and the point cloud, to the original image encoder and point cloud encoder, the model will perform very slow. It just cannot deploy on the robot. It just cannot do navigation, cannot do anything. But if we can divide the model into system 1 and 2, and we only fit the real-time data, for example, the high-frequency updated point cloud, right? It could be captured by the lidar, or you have the L2 lidar of the robot dog, right? And the egocentric views, that's from the sensor, right? That's from the camera, only fit into the small part of the model, just the system 1. But the overall scene fit into the original model, that's the system 2. So what's the overall scene? How can we do that? So what we can do is we store these real-time egocentric views, but we don't need to fit everything into the model. We only do the synchronized sampling. For example, if we find some key point of the scene, we store it, and we can then fit in this image sequence to the let's say to the system 2. So this system 1 and 2 can let's say it's a very good engineering design for adapting the foundation model to a very small robot. So this is a very small robot to let it navigate in the real scene. So here's some oh, by the way, also synthetic data. So if you try to adapt your 3D foundation model to something new, you also need to synthetic those data. For example, the previous model does not have any navigation data, so if you adapt it, it will fail. But if you're using the similar procedure to let the foundation model or let the language model to synthetic similar data, for example, here is a navigation COT. That's the output of how the Gemini Pro thinks where we should go. For example, given this historical view and current view, and the correct action prompt, right? You already know the ground truth of these data. You can gather from the public open source navigation data set, for example, HM3D. Then you can synthetic the chain of thought, right? The thinking chain of these results, like how these models should be think in order to get these correct results. So you can use those kind of thinking, the COT data, to train a foundation model. And yeah, similar, you can also use RLVR if your model is not satisfactory. For example, sometimes I do drawbacks a lot of time and need to predict very good paths from the beginning towards the endpoint. So I can do a endpoint and path reward. And also I want to, let's say I want to have a very good understanding of the scene. I can have an answer reward or semantic reward. So that's similar to the, let's say to the 3DR1 design, but in the embodied scene. And you can see our navigation model is not a pure navigation model. It can not only do the navigation, but it can also do the embodied dialogue, embodied reasoning, and planning. So previous navigation model, for example, the VLN model and object nav, can only do the navigation, but our model inherent the foundation model capability, so we can talk with the model and do reasoning and planning. So here's some, okay, it's working. So here's some results, yeah. So this is also a pre-scanned point cloud. So the only shortcoming of this model, the main shortcoming I believe is that because the limitation of our facilities, we haven't got the go-to robot yet at that time. So we are using a very tiny UGV, which means that I need to do the pre-scanning of the scene. But now, like we have a better LiDAR, we have the L2 LiDAR of the Go2 Pro. Then we probably can do it with in an on-scene environment. So that's the only problem. Yeah, and you can see that's the basically navigation with those inputs. Point cloud as input, depth as input, and ego center view. And this is the bird eye view. Yeah. So also, you can keep discussing the discussing with the model to do the embodied dialogue, but it just output is a little bit slow because it's a remote deployment. So the output is a little bit slow. And the reasoning as well, yeah. So basically, that's the we're trying to recording the real reaction time, and we make this demo. So basically, that's the waiting time. If we're asking this problem, it will wait like this. Yeah. So that's one application, and also you can do it on ARM type robot. That's an ECCV paper. So ARM type robotics, ARM type robot, for example, you want to deploy your visual language model onto a, I don't know, is that a friend? No. So onto a robot arm planning, you also need to address this problem, but your reward needs to be changed. For example, in ARM type VLA, the most important is the perception, which we call the affordance reward, and the planning trajectory of the robot arm. So you can have the trajectory reward, but the only problem is this one is in 2D. So we need to do the reprojection to 3D, and the performance decrease. So we try to address this problem to let it planning in 3D and that's a extension work. But yeah, but at least this one's working very well in 2D. So you can see here's some example. Okay, here's some example. Yeah. Basically, you can grab some banana and put it in the box. Do some simple object manipulation. Yeah. Yeah, basically that's the chain of thought we just output. For language model, this one is the chain of thought. Yeah. So so similar cases in mobile navigation, and manipulation. So if we have a go-to, like can we adapt our let's say foundation model into go-to? Yes. There's also ECCV paper, and similar architecture. Only the action decoder is different because you're adapting to a robot dog, and similar data synthetic pipeline. You need to synthesis similar data and do the RVR pre-training, RVR fine tuning. So you have a movement reward, you have action reward, you have a format reward to make sure language model always predict the correct format. And yeah, this one is basically the results. Yeah. So also this one is unseen environment, and this is the real-time point cloud prediction, because we haven't do any pre-scanning in this case, because we have a better lidar. Lidar is auto lidar on top of the robot. Yeah, in the front of the robot basically. So you could navigate it to the object and do just slow. It's just slow. Navigate to the and do some action. For example, I wanted to sit down and just sit down. Yeah. So.
How those tasks encoded? So what's the direction that you give to the robot for this type of actions?
Yeah. So I should navigate to the robot, right? So you can see. It's already in its visual perception, so it's not really a long horizon robot navigation. I haven't solved this. I believe it's a very hard problem. But yeah, so for the VLN and object nav, you have already seen this object, and I told the robot to moving forward to the moving close to the box and do some actions. So you give it one time query said moving forward to the box and sit down. And it will basically perform like this, yeah. Basically perform again, moving forward and just slow response, and it eventually sit down, yeah. Basically, yeah. So, yeah, that's something that I believe now the industry most interested about video world models. I believe Pi series like physical intelligence companies start to working on world model as well, because they believe that language models do not solve anything. It's true, because language models can only understand the abstract knowledge of human. It cannot understand what's going on in the visual world, what's the physical constraint of the world. So I don't trust language model as well. So is this method we develop in language models and language-based VLA can also be adapted to video world models that's based on the vision. So it's vision-centric, yes. And so this is a typical video world simulation work. So it's not really embodied, but it could be adapted to the simulation neural simulator. That's a very new topic that some people want to do. Use world model as a simulation to replace the traditional simulation, because traditional simulation is very slow and have a very large restriction on the device. For example, if you deploy like ASIC sim on a H100, A100, it will fail because it requires you to deploy on the RTX, right? So they're trying to use neural networks to replace the simulation. Yeah. So this is those kind of work. So how can we obtain these geometry? These geometry correct, or at least geometry as a reasonable and physical reasonable videos. So similar, we just design some RL signal. For example, reward signal. So the meta view score is basically the geometry score for testing if the geometry looks good. So this little queen logo means that it's a ROAIF. So we are using AI models, for example, the twin model, as a reward to training the video foundation model. And also the rendering score is basically PSNR, SSIM, stuff like that. And trajectory score is to compare the camera trajectory. I think camera trajectory to the ground truth trajectory to see if the model following the correct camera trajectory. So this is also the reward function. And there's also a general reward function that's been widely used in video generation because you can always gonna use. I think Professor Yue Wang has a paper called FID score, right? FID reward. Just using FID as a reward function and it will work. But yeah, there's a lot of other measurement for evaluating if the video looks good. So you can design this kind of reward and do some training. And eventually this can also work on the video simulation. So yeah. Yeah.
Right. So
yeah. So this one is too bright, but at least better than one, right? At least better than one. Yeah. One model is the Frontier video foundation model that we use today, and yeah. So different scenes you can generate, but yeah. But here's the problem. You can see every single video is very short. It's only 5 seconds. That's the main problem. Because if you want to do a simulation or doing a long horizon prediction with the word model, it must be generated like minute scale, right? At least minute scale. But the problem with the RL right now is that it's too expensive to train a 20 seconds or 30 seconds or even minute long video. So that's the main problem of this method. So that's exactly why I do not suggest to use RL to train from scratch, because it's too expensive. And even if you adapt to the video world simulation method and using the most frontier method, for example, dense GRPO, flow GRPO, you can only train a video with 5 seconds. So if you try to extend it to 20 or 30 seconds, the reward and the rollout time will be extremely long, and it's not really practical. So this issue will probably be addressed by the method I just mentioned called on-policy distillation. That's something I'm currently working, but yeah. Well, definitely that's the previous part is basically about how can we synthetic data with the large language models, and how can we do RLVR training. So in this in this paper or in this scenario, I'm arguing a new question: is that is language models always helpful? And if we have very agile or very generalized cool coding agent, for example, I think everybody is using coding agent right now, right? Using cloud or using Codex. Are these agents can be helped to scaling simulation data? I don't need those thinking chain of thoughts anymore. I have the very mature pipeline to synthesize thinking data. I need simulation data. I need robot simulation. How can we do that? So this words called code to words is using coding LMs to calling the render engine, for example, Blender or Unity as a tool to synthesize 3D and 4D assets. The main argument is it could synthesize temporal information as well. Because previously, if you're using GPT or cloud, it could only synthesize a static 3D object, for example, a wheelchair or a sofa that's located in the Blender engine, and you can somehow use these assets to your Isaac simulation, right? But it cannot synthesize 4D information. So code to words can give you a temporal, like dynamic object as well. For example, a moving object or a let's say moving characters or a articulated object, for example, a draw that can open and close. So I won't go through too much detail about that, but just gives you a overview, how can we synthetic data, how can we synthesis with the coding agent, is that we cannot treat every single component of the 3D assets or 4D assets generation as equal. There are always going to be a key point that's user more focusing on. For example, if we want to generating a leaves fall out from the tree, then the key component should be the leaves instead of the grasses or the tree, right? So we are more focusing on how can we generate a better tree leaves instead of generating better grass or better lighting. So there's an object string that's really focusing on how to generate better geometry and texture of the leaves, and the later part, the rest of the part, go through the scene string is generating the background information. So then you can have a very good 4D scenes that generated by these coding agents. So just totally coding agents, I want to fire in bushes, it will generate like this. And something like sunrise and sun goes down, and the scene, this all 3D. You can render into video. You can use it as a simulation assess into your simulation environment like SSIM or Mojoko. These are working, yeah. And there's a lot of different snow, even underwater. I know a lot of people are interested in underwater, right? You can also, but it's something like a UE engine, but it's more flexible than the UE because you can, all you need to do just tell the agent, I need those kind of things, and it will generate it fully automatic without any human in the loop, yeah. And is it going to work in Embodied? I'm currently working on, that's an SML paper, right? So I'm currently working on Kipami for really testing on an embodied simulation. Just a little bit progress, not too much progress, but you can see this this a GoTo, right? GoTo simulation walking on the rock, and this one is pushing a cone, I think, pushing something. Those are not in the Blender anymore. Those are in the simulation. Yeah. Right, something like that. Yeah. So the last, I think the last question of the fourth question is, what if we doesn't have a specified reward function? You know, we can always develop a very good reinforcement learning strategy if we can define a specified reward function, or at least a reward signal that we can use from RLHF or RLAF. But here's the problem: is that there's something that I know is correct and I know this is wrong. What's correct and wrong? I just cannot really define a very good function for that. So for example, I gather a lot of successful case and I gather a lot of failure case. I just know why it's failed. Like why it's failed. How can I develop a reward function can correct this? Is it possible that let the robot to learn itself by self-evolving? Yes, it does. And there's a way to do that called self-supervised reinforcement learning, and it's better to use when you're trying to deploy on a real robot on the real time. That's called online reinforcement learning. So these are always like show in the same time. So because if you're trying to do online reinforcement learning, then the most effective way is that do not give it a specified reward, but give it the correct pretest task. For example, if my pretest task can tell which part is the correct successful cases and which part is the failure cases, then I can learn from these data. So also easy to be paper called Evolve VLA. So here's the example that I know something. My robotics always working on grabbing a banana, but sometimes it just failed on opening a drawer, and I don't know how to develop a reward function for opening the drawer. And one way is that you're just collecting the successful drawer opening data and the failure drawer opening data, and also some hard negatives. Because if you're only training with positive and negative data, then it cannot solve the hard negatives. For example, my arm is approaching to the handle of the drawer, but it's just not open. So this is hard negatives. So you always want to include some hard negatives in your training paradigm and use it as a pretest task to train your model. So you can adapt a very traditional PPO training, and you will have a very good results even without a specified reward function. So this is the case, yeah. This is the case. So it's I think I think it's moving objects close to another object, right? So yeah. So the only problem is that it's a very new domain. Not really new, but compared to traditional RL, it's new. So not too much working on self-supervised reinforcement learning compared with the RHF and RVR and imitation learning. So I don't believe that in the current circumstances it will outperform the traditional RL. But eventually, these are definitely more promising and have more potential, because in the most cases we just don't know how to develop the correct reward function. So I believe like online reinforcement learning with SSRL will be the future way to address those kind of problems. Yeah. So here's some takeaways, I think, before I'm closing my talk. But you guys can feel free to ask any questions once I finish this. So here's some takeaways. Synthetic data and data-driven methods are the key to achieve scalability and generalizability. I think everybody knows that. Rich Sutton knows that. He wrote a bitter lesson, right, talking about this. Just go for a data-driven method. That's everything know that. Everybody know that. And the second part is do not abuse reinforcement learning for post-training. Use RL only to adjust foundation models. DeepSeek R10, which means training RL from scratch, now have been shown is not really successful. So, and I have given you a very concrete example that RL is very expensive. The word model with RL can only generate 5 seconds video. That's a very concrete example. So do not use RL for training from scratch. It will wasting your time. It will like landing a not really good model, but try to use the generalizability of the foundation model, and you're building RL on top of that. Yeah. So the third part is, I know everybody's working on language models nowadays, but not in ACFR. I mean, ACFR is still working on robotic planning, right? But yeah, nowadays industry, 90% people, if you go to Bay Area, people working on language models, and the problem is that language models that perform next token prediction will not achieve advanced machine intelligence. I think that's what LeCun said, right? And I believe part of his claim is correct. At least this part is correct. So LLMs doing next token prediction, I mean, this is not gonna understand the real world scenario. So if you're interested in human level intelligence, so do not solely focusing your time on LLMs. Instead, try to find a method that can really understand the spatial awareness. For example, building your models on visual modality, building your model on the touching sensors or other sensors, but not totally focusing on language models. So language models will probably eventually not totally understand the physical world. So that's the last claim. So basically, yeah. Thank you. Yeah. So any questions? It's a lot of work, and I'm not going through any too much details of each work. So because I want to give you guys a overview, like how can we paving a path towards a generalizable robotics, and this is something based on my background, because I'm not a RL guy, I'm not a robotic guy, right? So I'm doing this from a CV guy who is currently working on, who's previously working on representation learning, and try to solve this problem via learning-based method. I believe, like most of these cases, for example, manipulate a cube has already been solved by traditional robotics, right? Even back in like 1990s, people started working on like visual servoing. They can still doing better tasks than VLA. But why we still working on VLA or word models, I believe, is for generalizability. And we wish to see, at least some part of the community wish to see, that if we can somehow found the scaling trend, like language models, and adapt the scaling trend to embodied intelligence. I think that's the reason why people started working on VLA and word models. Thank you.